You ever notice how the same patterns seem to pop up in totally different places? Well, in math, it happens all the time. For decades, mathematicians kept seeing these similar structures in geometry and algebra and logic, but they didn't have a common language to talk about them. So let's dive into the solution they came up with: category theory. At its heart, category theory is all about seeing the forest for the trees. I mean, whether you're working with geometric spaces or algebraic groups, you start seeing the same kinds of relationships over and over. The big idea here is to focus on the processes, the transformations, which it turns out can be visualized with just simple diagrams of arrows. But, how do you formally capture that feeling of similarity? How do you prove something about structure itself once and for all? So this really is the central question. What is the common thread that links all these different mathematical worlds? I mean, on the surface, they seem completely different, right? A group is all about symmetry, a topological space is about what's near what, and a set is, well, it's just a bag of stuff. The answer, it turns out, lies not in what these things are, but in what they do. And this brings us to the really foundational, almost philosophical shift that category theory proposes. It asks us to stop obsessing over what's inside an object, the elements of a set, the points in a space, and instead to focus entirely on the relationships between the objects. It's a language built not on things, but on transformations, on arrows. So what is a category exactly? Well, it's built on a few surprisingly simple rules. You've got objects, just think of them as dots, and you have arrows going between them. The first rule is that you have to be able to follow one arrow after another. That's called composition. And this whole process has to be associative, which really just means it doesn't matter how you group the steps in your journey. Finally, every single object needs its own identity arrow, basically a do-nothing loop from itself back to itself. That's it. That simple framework is a category. This leads to this really profound idea: learning to live without elements. What that means is we can understand an entire system just by looking at its web of connections. We don't need to peek inside the dots at all. All the crucial information is actually encoded in the arrows and how they fit together. This is the absolute core of the categorical way of thinking. And you can see how this abstract idea just applies almost everywhere. The world of sets and functions, that's a category. The world of groups and their special structure-preserving maps, called homomorphisms, yep, that's another one. Topological spaces and continuous maps, you guessed it, another category. Each of these mathematical universes, with its own specific type of object and its own type of arrow, fits perfectly into this one single unified framework. Okay, so we've set up all these different worlds, these categories, but that's only half the story. The real power, the real magic, comes when we can build bridges between them to see how the structure of one world translates into the structure of another. And that bridge is called a functor. It's a map between categories. It sends objects in one world to objects in another, and arrows to arrows. But here's the crucial part. It has to respect the structure of all those connections. If you can get from object A to C through B in the first category, your functor has to map that entire path faithfully into the second one. It's like a perfect, structure-preserving translator. Let's look at a couple of powerful examples to make this real. There's a functor that can translate the world of rings, think number systems where you can add and multiply, into the world of groups by finding all the matrices you can build from that ring. Then there's another functor that acts like a simplifier. It can take any complicated group and find its most basic commutative version, where the order of operations doesn't matter, by basically filtering out all the complex parts. So we have worlds, which are categories, and we have bridges between them, which are functors. But, category theorists, they didn't stop there. They asked the next logical, if slightly mind-bending question. What if we have two different bridges between the same two worlds? Can we actually talk about a relationship between the bridges themselves? And the answer is a big yes, and it's called a natural transformation. This is a map between functors. So if you have two different ways of translating a structure, a natural transformation is a process for shifting from one translation to the other, but in a way that's consistent everywhere, without any weird arbitrary choices. It's the natural way to compare the two bridges. It's a transformation of transformations. So you see how this builds this beautiful conceptual ladder, right? First, you define a category to formalize the whole idea of a mathematical world. Then, you use that definition to define a functor, which is a bridge between those worlds.
And finally, you use functors to define a natural transformation, which is a structured relationship between those bridges. It all stacks up perfectly.
And that entire ladder, it turns out, was built for a very specific reason. This really brings us to the punchline, and it comes straight from the founders of the subject, Eilenberg and MacLane. This was the whole point. The entire intellectual structure was built for one primary goal: to get to a formal, rigorous definition of a natural transformation, to capture exactly what it means for two mathematical constructions to be related in a way that feels totally consistent and universal. Okay, so we've climbed this ladder of abstraction. What do we get for it? What's the payoff? What does this new language actually let us discover? Well, one of the most powerful and just everywhere concepts it unlocks is the idea of an adjunction. An adjunction is this special relationship between two functors that are going in opposite directions. You can think of them as a perfectly matched pair. One of them, the left adjoint, is often a constructor. It freely builds the most general, rule-abiding structure possible from something simpler. For instance, taking a set of letters and creating the group of all possible words you can make. Its partner, the right adjoint, is a forgetful functor. It does the opposite. It takes that complex structure and forgets all the rules of grammar just to see the simple underlying alphabet again. And this is not some rare exotic thing. As Saunders MacLane himself wrote, the slogan is, "Adjoint functors arise everywhere." This pattern, this duality between constructing structure and forgetting it, is one of the most fundamental recurring patterns in all of mathematics. And adjoint functors finally give us the precise language to talk about it. And all these powerful ideas, categories, functors, and adjunctions, were laid out formally by MacLane in his absolute classic text, Categories for the Working Mathematician, a book that really brought this new way of thinking to just about every field of mathematics. So let's just do a quick recap. Category theory gives us this universal language to talk about structure, and the key is it shifts our focus from objects to the relationships, the arrows between them. Functors are the bridges connecting these different mathematical worlds, and natural transformations let us compare those bridges. And this whole framework lets us spot these profound universal patterns, like the beautiful duality captured by adjoint functors. Which leaves us with a pretty fascinating final thought. We started by looking for a way to talk about patterns inside of mathematics, but this language is so general, so fundamental, that it's now being used in computer science, logic, physics, even linguistics. So the real question is, what other deep hidden structures out there in the world are just waiting to be described by the language of arrows?